Differential equation arises in variety of areas such as engineering sciences, physical sciences, chemical sciences, etc. When you consider freely falling body of mass m, when you apply Newton's second law of motion, if the body is falling from a height y above the ground, we have the equation m times d square y by dt square equals minus m times g, where g is the acceleration due to gravity and m is the mass of the body which is falling. We have the differential equation d square y by dt square equals minus g, which follows from this equation. We have this equation involves the derivative term d square y by dt square, which is the second order derivative of unknown function y with respect to independent variable t. Similarly, if you consider another situation of spring-Marx equation, the force acting on the spring due to the weight of the body can be computed using Newton's second law of motion, and we have force F equals m times d square y by dx square. By Hooke's law, we have force F equals minus k times y. When we equate these two RHS, we obtain m times d square y by dx square equals minus k times y, from which we have the differential equation d square y by dx square plus omega square y equals 0, where omega equals root of k by m is the angular velocity. In this differential equation, we have d square y by dx square is the derivative term, which is the second order derivative of dependent variable y with respect to independent variable x. In general, we can say that an equation involving independent variables or dependent variables and at least one derivative term will be called as the differential equation. The existence of independent variables and dependent variables as terms is just an optional case. However, at least one derivative term should be present in the equation, then only we can call the equation as differential equation. If you have a differential equation involving only ordinary derivatives with respect to single independent variable, we call the differential equation as ordinary differential equation. Suppose you have a differential equation involving partial derivatives, then we call the equation as partial differential equation. We come across partial differential equation when we learn about heat equation and wave equation. Recall that order of differential equation is the order of highest order derivative present in the equation, and degree of the differential equation will be power of highest order derivative in the equation. For example, in this equation, we have the highest order derivative is d square y by dt square. Hence, order of the differential equation will be 2. Since the power of this highest order derivative is 1, we have this equation is of degree 1. If you consider the second equation, here we have the highest order derivative is d square y by dx square. Hence, order of the equation will be 2. Since the power of highest order derivative is 1, we have degree of this differential equation will be 1. Let us discuss about linear ordinary differential equation with constant coefficient. When you consider nth order ordinary differential equation, we have the general equation written as a0 times d raised to n y by dx raised to n plus a1 times d raised to n minus 1 y upon dx raised to n minus 1 plus etc. plus an times y equals capital X, where RHS capital X is a function on single independent variable x, and we have a0, a1, a2 etc. are constants. This term d raised to n y by dx raised to n is the nth order derivative of y with respect to independent variable x. Similarly, we have d raised to n minus 1 y upon dx raised to n minus 1 indicates n minus 1th order derivative of y with respect to independent variable x. If you have the RHS as 0, then we call the equation as homogeneous linear ordinary differential equation. Whenever we have RHS capital X not equal to 0, we call the equation as non-homogeneous linear ordinary differential equation. We have the differential operator notated using capital D equals d by dx. When we rewrite equation 1 using this differential operator, we can replace d raised to n y by dx raised to n using capital D the whole raised to n. Similarly, d raised to n minus 1 y upon dx raised to n minus 1 can be replaced using capital D the whole raised to n minus 1, and so on. Thus, we have all the derivative terms can be replaced as powers of this differential operator capital D. Thus, we have equation 1 rewritten as a0 times d raised to n plus a1 times d raised to n minus 1 plus etc. plus an times 1 applied on y, which equals the RHS capital X, where capital X is a function on independent variable x. If you consider this term d raised to n y by dx raised to n, you can consider it as d raised to n acting on the input y. Similarly, when you consider this term d raised to n minus 1 y upon dx raised to n minus 1, you can consider it as differential operator d raised to n minus 1 acting on input y. That is, when we introduce differential operator here in the LHS of this equation, we have y is a common input to each term, and that is how you have a y appearing here, which is a common input to all the differential operators. D raised to n is differential operator of order n, d raised to n minus 1 is differential operator of order n minus 1, and so on. You can even consider this expression as a polynomial in terms of capital D, and hence you can rewrite this equation as a function on differential operator D acting on the input y equated to RHS capital X. The homogeneous equation corresponding to this equation will be f of d acting on y equals 0. Since f of d is an nth degree polynomial, we have this polynomial will have n roots or n solutions. That is, considering f of d acting on y equals 0, we have the solution y equals c1 times f1 of x plus c2 times f2 of x plus etc. plus cn times fn of x will be called as the general solution, where c1, c2, c3 etc. cn are the arbitrary constants. Actually, we have y1 equals f1 of x, y2 equals f2 of x, etc. yn equals fn of x will be the solutions. Since we have n linearly independent solution for f of d into y equated to 0, we will have any linear combination of these n linearly independent solution will also be a solution to the differential equation, and this principle is known as superimposition principle. That is, when you have f1 of x, f2 of x, etc., fn of x are solutions to the nth order differential equation f of d acting on y equals 0, we have sum of some scalar multiples of these linearly independent solution will again be a solution. Hence, we have general solution given by y equals c1 f1 plus c2 f2 plus etc. cn fn, where f1 f2 etc. fn are functions on independent variable x which are linearly independent solutions. Whenever we try to solve the homogeneous equation f of d acting on y equals 0, we obtain complementary function. That is, this expression can also be called as complementary function. For a homogeneous linear differential equation, we will have general solution coinciding with complementary function. But this is not the case for a non-homogeneous linear differential equation. Suppose you have RHS capital X is not equal to 0. In the equation f of d acting on y equals x, then we have another part also for the general solution, which will be called as the particular integral. When we solve homogeneous linear differential equation, general solution will be complementary function only, but when we solve non-homogeneous linear differential equation, we will have general solution will be sum of complementary function as well as particular integral. In order to find out particular integral is also known as particular solution, we have to make use of RHS capital X, which is a function on small x. When you consider the equation f of d acting on y equals capital X, when you operate 1 by f of d on capital X, you obtain particular integral. We will be studying certain general rules in order to find out complementary function as well as particular integral for different types of differential equations.